I'm Brian. Today I'll be talking about explaining visual changes in web interfaces. This is work done at the University of Washington with my co-authors, Andy Ko and Mike Ernst. So one of the great things about the web platform is, what's going on here? Oh, I see. Well, they look the same, so there you go. Sneak preview. Okay, one of the great things about the web as a platform is that it's all open source. So if you want to understand how the UIST web page works, you can right-click and go look at the source. So if you're learning and you want to see how something is implemented, like this cool hover effect or the drop-down menus, you can hypothetically go look at all the source code and read through it and know how it works. Unfortunately, it's a little more complicated than that. But hypothetically, you could go and see how all these effects are implemented. So in the software engineering literature, this is called feature location. The idea is you have some feature, but you need to find the code that actually implements it. In this talk, I'll be focusing on feature location for interactive web content. This is things like the UIST website and its effects, galleries of shiny products, web games that happen to be implemented with the DOM, and how we can support feature location. So when you're doing feature location, there's some stereotypical questions that we want to support. The most obvious one is, how does it work? How do I interact with this thing? And from a user perspective, this is pretty easy to do. You poke at the website. You have some idea what the visual states are. And the second question might be, well, okay, how is this effect achieved? There's lots of different ways to do stuff in the web. You can have DOM and CSS, Canvas, WebGL, etc. So to do this, you need to go inspect the page and see what's going on. But ultimately, that state has been set up by some other code. So you also need to figure out what JavaScript is running to achieve these effects. And this can be really hard because your average website has like 2 megabytes of JavaScript. And that's a lot of code to read. So in this work, we're addressing some shortcomings in each step here. So for visual output, we don't have a history of the output. So if there's more than 2 states, or they change quickly, it can be really hard to even figure out what the states are. For DOM and CSS, there could be a lot of DOM elements that represent one fairly small widget on the page. And each of those elements can have CSS. So there's a lot of state, and only a small fraction of that is relevant to some interaction. And there's no link between this small amount of state and the code that messes with it to implement some effect. So this is hard to link these together. So Scry is a tool for staged interactive feature location for web content. So the way Scry works is that as some widget is changing, it will take some snapshots of the different visual states. A user can select 2 of these snapshots, and Scry will compute a diff of these 2 things in terms of the DOM and CSS that was used to render this. So once the diff is being shown, a user can interactively go in and select some part of the diff. And when they do that, they will see a list of mutation operations that were responsible for setting up the state change that they selected. So we'll go into this with an example. Here's this National Geographic article, and there's this little search button. You click on it, it'll expand out. You can type into it. If you click it again, it will hide. So how does this work? The first thing we need to do to investigate this with Scry is to find the root element of the widget. And we do this with most tools by right-click, hitting inspect. And once you've done that, you can see in the developer tools on the left, a DOM tree. If you find the root element, you can right-click it, and there's an option called track element, which is a new Scry feature. And once you do that, as the page and that element changes, Scry takes snapshots automatically of the different visual states. So if we zoom in on the left here, we can see some of these states in a film strip type interface. So if we adjust the view here a little bit, we can see more specific states. And you can see, the search bar contracts and gets more transparent over time. So you can select any of these states and see the DOM and CSS that produce that visual output. So you can see over time, the width might change. What if you could just select 2 of them? So if you do that, Scry will show these 2 states side by side. Well, not side by side, but close to each other. And you can see that the width has changed between these 2 states. But it seems the top one is darker. So we can drill down in the DOM tree and find, maybe there's some other element that has an opacity change. And in this case, there's an input form element, and that's the one that has a different opacity over time. So here we can drill down into the DOM in these 2 different states and compare it directly to see what nodes implement what visual features. So I'll move on to a second example. In this example, there's a Tetris game that's implemented on the web somehow, and we want to understand how it works. So the first thing we need to do is to find the game board element and right-click it and say track element. Then we're going to go over to the game board and interact with it a little bit to produce some states in the Tetris game. Then we want to go dig into some more. So once we've done that, we can stop recording. We go over to the left and go back to that film strip interface. So there's 2 main moves in Tetris. You can translate and rotate. So first we'll look at translation by finding a pre and post state for a translation move. Once we've selected those, we can go down and see what's different in the DOM between these 2 states. And it seems like there's just a container element for one piece, and it's been changed with absolute positioning. That's pretty straightforward. What about rotation? So we can do the same thing, find 2 states, see them in the diff interface, and it's hard to see with the color here, but on the top, all the sub-elements of the piece have been removed, and on the bottom, they've been added back. So it seems when a piece is rotated, it just gets rebuilt out of little blocks. If we want to see the code that's responsible for doing that rebuilding of a piece, we can click on one of the diff markers, and that will show a list of all the mutations, inserting an element, setting an attribute, and so forth. They're responsible for rebuilding that piece. And if we click on one of these specific operations, we can see the source code in the call stack that did that specific operation using a DOM API, like append child, set attribute, and so forth. So that's Scry in a nutshell. And now we'll dig into a few of these pieces here to explain how it works. So first, Scry needs to take these snapshots, but in order to take a snapshot of the output and also the input, we need to know what could possibly affect the visual appearance on the page. In the web, there's 2 main things. There's the DOM tree, which is sort of like a model of the UI. And there's also CSS style properties, which affect how the model is rendered. So this can control things like the color, the font, absolute positioning, and so forth. Both of these get fed into your favorite rendering engine, and it implements a specification to produce some screenshot. So we need to be able to capture all of these things in order to know exactly why some visual state has changed. So in a snapshot that Scry captures, there's the DOM subtree for the element that we've selected, a screenshot of the element, computed styles and rules that apply to nodes within that tree, and also a trace of mutation operations since the last snapshot that help us understand how the state has changed. So why does the visual state change at all? Well, now we have this snapshot, and it has outputs and inputs. We need to be able to see how the inputs differ. On the left side, you can change a DOM tree through tree operations like insert and delete. You can reorder siblings. You can set states like hover and focus. And you can also change the style properties by adding rules, doing animation, which will programmatically change a property over time. So we need to capture these things or be able to detect these changes. So, Scribe could just interpose on every single one of these mutations or property changes, but there's a lot of them. And most of them don't actually cause any visual changes. So what Scribe does instead is it works backwards from changes to the visual output. Scribe has hooks into the rendering engine, and the rendering engine can tell us pretty cheaply every time some rectangle is painted on the screen. And we know where the target element is. So if we intersect a notification, something was painted. If that rectangle doesn't intersect the thing we care about, then it definitely didn't change appearance. If it did intersect, we do a visual diff to make sure it wasn't like some rendering artifacts like anti-aliasing, If it's still significantly different, we take a full snapshot of the DOM, CSS, and screenshot. So if we need to compare these two snapshots, Scry uses a pretty simple algorithm where it takes these two snapshots side by side and it has a stable identifier for each DOM element in the two snapshots. So it goes pairwise. It looks at element in snapshot 1 and 2 and see if it is in a different position in the tree. Does it have different properties? Is it missing in one or the other? And so forth. And then it makes a diff view from that diff it did. So next, if we have a specific diff operation, and we want to see the mutation operations that are responsible for the style changing, what Scry does is a straightforward application of slicing to this trace of mutation operations. So if you imagine some mutation operations on a tree, like you change an attribute, that will depend on that node actually being inserted into the tree. So there's some dependencies between these tree operations. And what Scry will do is make a dependency graph of these. And for some specific operation the user has selected, like an attribute change or a new node, Scry will find an operation in the dependency graph that corresponds to that change and then find everything that that depends on. So it computes a slice of this dependency graph and presents that to the user as a list of operations. And each operation has a call stack, so we get the source location for free. So there are a lot of interesting technical challenges in trying to do this with real web content, which does wacky things. The first thing we ran into is that the way a user sees an element is often very different from what the browser perceives. So in the search box example, on the top is what the user would see, and the bottom is what the browser would see. The search box doesn't have a background itself. That's of the body of the page. So we want to diff just the transparent thing and the solid input box. But if you showed that to the user, they would be like, this thing doesn't exist on my page. There's no checkerboards. So you need to take more than one snapshot, depending on what you're using it for. A technical issue is that a lot of browsers use hardware acceleration for animations. So if you want to take a snapshot on each animation frame, you need to turn that off somehow, which can be tricky. A thing we've run into with newer libraries like React is that it breaks the way Scry does comparisons of snapshots, in that we rely on some node in a heap having a more or less stable identity in terms of like what it represents in the UI. And a library like React doesn't preserve that at all. It's a box of Legos or DOM elements, and the user says, I want my UI to look different. It will take these elements randomly out of its box of Legos and sort of like rebuild it. And they might have no correlation to what it was built last time. So in this case, Scry could fall back to a tree diffing algorithm. There are lots of these in the literature, and it would be a decent substitute. We have call stacks for all these mutation operations, but a lot of the times people use jQuery to do all their mutations. So this makes the call stack a lot less useful for disambiguating parts of the code. You'd have to look up 5 or 10 frames or whatever to find the actual user code. And lastly, most of the styles and attributes on a web page don't do anything. So it would be great if Scry could just prune those out by seeing if removing them actually changes the visual output. So to conclude, Scry does feature location by presenting visual states to the user. These can be captured automatically and pretty cheaply. In the user interface, Scry will juxtapose the captured inputs and outputs for a single state. And we found that looking at these together can help you understand both sides. And lastly, we use diff markers as a new way to filter through these mutation operations so you can only see the relevant things for some specific change that you're interested in. And with that, that's all I have. I look forward to your questions.
Increasingly, we're seeing a bunch of web programming happen in what you might almost call like higher level frameworks.
So I haven't looked at it specifically, but so yeah, Scry does look at sort of like the reality of what the browser sees, not like what someone developing the app might see in Angular, React, or whatever. I do think if we add some domain-specific knowledge, that we could go back to that. But, I mean, it depends on the use case, too. If you're using this to debug, that would be really useful. If you're using it to look at apple.com, like, well, you don't really know what the Angular stuff is anyway, you know. Oh, I see. So I think there's different affordances that we could add that would support understanding why it didn't something happen. This is very much about what did happen.
Okay.
For example, there's lots of styles that do nothing. Or you might add a new style and nothing occurs. Well, why did that happen? That might be a separate project, but even just highlighting what styles are completely useless would be really helpful for debugging. So I think it's sort of complementary what you could do for debugging with this.
Michel Baudouin-Lafont, that works. Université Paris-Sud, Paris-Saclay, it's great work. I was wondering if you thought about having a way to put breakpoints on either the visual interface or in the CSS or something, so you don't have to do this searching through your history to look at the stuff you're interested in.
Yeah, so you can think of the way Scry does it now as sort of a breakpoint on a specific element in its subtree. It will capture snapshots for that, but it won't direct you right into the tree to that specific state. I think that would definitely be possible. This just wasn't a use case we looked at so far.
Cornell from, Dong from Cornell. Can I obfuscate my web page against the Scry? Obfuscate.
I mean, you can make the JavaScript really hard to follow, so it would be hard to necessarily understand the logic involved, but in terms of the DOM and CSS, like, no, you can't really obfuscate it because this is what the browser looks at to render your page.